Hi there, welcome to Sleep Stories Universe. You made it to the end of the day. Get comfortable, however your body wants to rest right now. Tonight we're going to find something that can't be seen, and we're going to find it together, one quiet clue at a time. You don't need to memorize anything tonight. You don't need to follow along perfectly. Just let the words carry you. Tonight's story is The Invisible Evidence, how we found a black hole we couldn't see. We'll follow the clues gently, from the motion of stars, to bending light, to glowing matter, to the faint ripples that move through space itself. And if you drift off somewhere along the way, that's perfectly fine. Let's begin. Here's the thing about some of the most important discoveries in science. They didn't always come from looking directly at something. Sometimes they came from noticing what was missing, from watching how other things moved, how light bent, how stars swung in wide arcs, and asking very quietly, what could possibly be causing that? That's how scientists have come to understand black holes. Not by seeing them directly, but by reading the effects they leave on everything nearby. You can't hold a shadow in your hands, but you can know it's there. And that's exactly where science begins. Let's start with the most honest thing we can say about a black hole. It doesn't look like anything. Not from the outside, not with your eyes, not with an ordinary camera pointed at the sky. A black hole gives off no light of its own. It doesn't shine. It doesn't glow the way a star does. If a black hole were floating alone in empty space, and you tried to find it, simply by looking, you would see nothing at all. So why do we believe they exist? That's the whole story, really. And it's a beautiful one. Let's take it one step at a time. Here's the simple version. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape once it crosses a certain boundary. That boundary has a name. It's called the event horizon. Think of the event horizon as a point of no return, not a wall, not a surface you'd crash into, just a threshold. An invisible line in space where the rules quietly change. Before it, escape is at least theoretically possible. Beyond it, escape is not. And because light itself cannot escape from within that boundary, the region inside appears completely dark to any observer on the outside. No light comes in and stays, and none comes out. A black hole, in the most literal meaning of those two words. Here's a way of thinking about it that sometimes helps. We're not talking about something that absorbs light the way a dark surface absorbs light. We're talking about something where the very shape of space, the geometry of the paths that light travels on, curves so completely inward that there simply is no outward road anymore. That's a different kind of darkness, a quieter, deeper kind. But let's not rush ahead. Let's stay here for a moment. The event horizon, just a boundary, not a wall. The event horizon is one of those ideas that sounds more dramatic than it perhaps needs to be. It is a boundary, a threshold. In theory, if something were crossing it from outside, which no human has done or could safely do, there might not be any dramatic physical sensation at the precise moment of crossing. What changes at the event horizon isn't necessarily what you feel. What changes is what is possible. Outside the event horizon, light can travel outward. A beam of light can, at least in principle, make its way back out into the wider universe. Inside it, every possible direction, including what we'd call outward, curves back inward. Light cannot escape. Information cannot escape. Nothing carried on any electromagnetic wave can cross that boundary from the inside out. It's okay if this feels abstract. You don't need to picture it perfectly. And honestly, the mathematics of this stretches well beyond what any picture can really capture. Just let the shape of the idea rest with you. A point of no return. That's the heart of it. Why we can't see a black hole directly. So now we have this region of space that emits no light of its own, surrounded by a boundary from which no light escapes. If we try to look for a black hole the way we look for a star, pointing a telescope at the sky and waiting for light to arrive, we come up empty. There is genuinely nothing to see. And this is not a problem with our equipment. This is not something a more powerful lens would fix. No optical telescope, no matter how large or sensitive, could give you a direct image of a black hole itself, because there is no light coming from inside it to form an image with. What scientists have learned to do, and what they've been doing with growing sophistication for several decades, is to look for the effects a black hole has on everything around it. The space around a black hole is full of motion, heat, extreme radiation, and dramatically bent geometry. And all of that is, in principle, observable. The indirect approach, the fingerprint approach, it turns out to be extraordinarily powerful. We'll spend the rest of tonight following exactly that. 4 separate fingerprints, 4 different kinds of evidence. But first, let's put one more piece of foundation in place. The 3 kinds of black holes. Not all black holes are the same. There are at least 3 broadly recognized categories, and it's worth spending a few minutes here, because each one comes from a different story and leaves different kinds of fingerprints. The first kind is what's generally called a stellar mass black hole. The evidence strongly suggests these form when a massive star, far larger than our own sun, burns through its fuel over millions of years and can no longer support itself against gravity. When that support collapses, the core implodes. Sometimes the outer layers of the star explode outward in an enormous burst of energy called a supernova. Under the right conditions, what remains at the center may become a black hole. Stellar mass black holes are heavy by everyday standards, but not extraordinarily so on a cosmic scale. A handful of times the mass of our sun, up to a few dozen times, roughly speaking. They're thought to be scattered throughout the galaxy, but most of them are dark and produce no observable light on their own. How many exist? The honest answer is that we have reasonable estimates but genuine uncertainty, and the specific, well-sourced number isn't one we'll offer here. What matters for our story is simply that they exist, silent and invisible, distributed across the Milky Way. Then there's the other extreme. Supermassive black holes. These are something else entirely. Millions of times the mass of our sun, sometimes billions of times. And the evidence suggests that nearly every large galaxy we've studied closely has one sitting at its center, including our own galaxy, the Milky Way. At the center of our galaxy sits a supermassive black hole called Sagittarius A star. In spoken language, simply Sagittarius A star. We'll follow its story very closely in the next chapter, because the way astronomers confirmed its existence is one of the most patient detective stories in modern science. Between stellar mass and supermassive lies a third, less certain category: intermediate mass black holes. These would fill the middle ground, larger than a stellar mass black hole, but not reaching the extraordinary scale of the supermassive ones. Here's what we can say with confidence. The evidence is suggestive, but not yet definitive. Scientists have found candidate objects, intriguing hints in the data, but it's honest and accurate to say that intermediate mass black holes remain an open, actively studied question. It's like looking for a missing piece of a puzzle, one that we think should be there to complete the picture, though we haven't quite held it in our hands yet. Not every chapter in science is fully closed. That's not a weakness, it's what makes it science. The formation mechanisms of supermassive black holes are also still an open question. How does something millions of times the mass of our Sun come into being? Several ideas have been proposed, but the evidence has not yet settled clearly on one answer. We'll acknowledge that honestly throughout this episode, wherever the ground is still soft. What's actually inside? Let's address something gently, because it comes up and because it deserves a careful answer. What's at the center of a black hole? General relativity, the best framework we have for describing how gravity works at large scales, predicts a point of infinite density at the center. This point is called a singularity, but here's the honest version of that. Most physicists don't take the infinite density part literally. When a physical theory produces an infinite result, it's generally understood as a signal that the theory has reached its own limits, that it's being applied to conditions it wasn't designed to handle. A singularity, in this interpretation, isn't a precise description of what exists at the center. It's more a sign that we need a better theory, one that weaves together general relativity and quantum mechanics in a way we haven't yet fully achieved. There are many ideas about what such a theory might say, but they remain ideas. They are not settled. So when someone asks what's truly physically inside a black hole, the most accurate and honest answer we can give is, we don't know. Our best theories stop making reliable predictions there. And that's not a failure of science. That's a map with an honest edge, carefully marked. Here is where our current knowledge ends. The region just outside, where things become detectable. Here's the part people often miss. When we say scientists can detect black holes, study them, measure them, learn from them, we don't mean they're somehow seeing inside. Everything we can observe comes from outside the event horizon. That region, the space just beyond the boundary, is where things become observable. It's where infalling gas and dust get compressed and heated to extraordinary temperatures and radiate energy outward. It's where light rays get bent by the extreme curvature of space-time. It's where gravitational effects reach outward across vast distances, gently altering the paths of stars across the sky. The inside of the event horizon is, in all likelihood, permanently inaccessible to any observation using light or any other electromagnetic signal. But the outside speaks. Clearly, in fact, once you know the language. A quiet correction. Black holes don't vacuum up everything. Before we move on, let's gently set aside one of the most persistent misunderstandings about black holes. They don't suck in everything around them, not in the way people sometimes imagine. A black hole doesn't exert some additional, special, extra hungry pull that ordinary gravity doesn't have. Gravity is gravity. If you were to replace our sun, which, to be clear, will never become a black hole, With a black hole of exactly the same mass, Earth's orbit would be completely unchanged. The pull would be identical because the mass would be identical. We'd have a much darker solar system, but the planets would keep right on orbiting. What makes a black hole extreme is not a different kind of gravity. It's that an enormous amount of mass is compressed into an incredibly small region of space. That compression means you can get very, very close to all that mass, far closer than you ever could to a normal star. And the closer you get to a concentration of mass, the stronger the gravitational pull becomes. Black holes are not hunters moving through the galaxy. They're extraordinarily dense, extraordinarily massive regions of space, with an invisible boundary and remarkable effects on the things that happen to come near them. That's it. That's the whole thing. Looking ahead, the fingerprints will follow. So, we know what a black hole is. We know why it's invisible to direct observation. We know what varieties exist and where the questions remain genuinely open. And we understand that everything detectable, everything observable, happens outside the event horizon, in the region where matter, light, and gravity all interact in extreme and measurable ways. Scientists cannot look inside, but they can read everything written on the outside. 4 fingerprints, 4 separate lines of evidence, each developed through decades of careful observation and each pointing from a different direction toward the same conclusion. The evidence, taken together, is strongly and consistently in favor of one thing. Black holes exist. Now gently, let's zoom out and follow the first fingerprint. Orbits. How invisible mass reveals itself. When something moves in a circle, something else is pulling it. And sometimes, what's doing the pulling is the most extraordinary thing in the galaxy. Let's talk about orbits. Most of us learn, at some point in our lives, that Earth travels around the Sun, that the Moon travels around Earth, that planets trace their paths year after year, century after century, in predictable arcs through space. And somewhere along the way, we learn that gravity is responsible for all of that. But there's something deeper hiding in that simple fact. An orbit isn't just a path. An orbit is a clue. If you watch something orbit, if you observe its speed, its shape, how long it takes to complete one full loop, you can work backwards mathematically and calculate the mass of the thing it's orbiting around. You don't need to see that central object. You don't need to touch it, photograph it, or measure it directly. The orbit tells you. The motion is the message. This is the first fingerprint, and it's one of the oldest, most reliable tools in all of astronomy. How orbits carry information, here's the simple version. The way gravity works, the stronger the pull at the center of an orbit, the faster the orbiting object needs to move to avoid being pulled inward. And the orbital path, its shape and period, encodes that relationship precisely. A very massive object at the center produces a strong pull. Objects orbiting it closely must travel quickly to stay in orbit. A less massive object produces a weaker pull, and objects orbit it more slowly. This relationship between orbital speed, orbital size, and the mass at the center follows well-established physics. It's the same logic that has been used for centuries to understand how planets move through our solar system. Within the framework of general relativity, the same reasoning applies, with refinements, even in the extreme gravitational conditions near a black hole. And here is the key insight, the one that makes this fingerprint work even for invisible objects. You don't need the central object to emit any light. You don't need to detect it directly in any way. You simply need to watch what orbits around it, carefully enough, long enough, precisely enough. And the mass at the center reveals itself through the motion it creates. This is how astronomers turn their attention to the center of our own galaxy. The galactic center, a busy, extraordinary place. The center of the Milky Way is not an easy place to observe. Between us and it lies a dense region of gas and dust that blocks ordinary visible light almost entirely. For a long time, the galactic center was simply hidden from view, obscured by the material between us. Infrared light, a longer wavelength of radiation, travels more freely through that intervening dust than ordinary visible light does, and infrared telescopes were able to peer through that veil and observe the stars moving at the heart of our galaxy. And what they found, over years of careful watching, was motion. Purposeful, dramatic, unmistakable motion. Stars orbiting something at the very center of the galaxy. Not drifting loosely the way you might expect stars to drift in open space. Orbiting, tightly, quickly, with the curved, elliptical paths of objects held in the grip of something enormously massive. That something had no detectable light, no visible form, no emission that any telescope could find, and yet the stars moved as if it were there. The patient detectives, Gez, Genzel, and the galactic center groups, this is where the detective story earns its name. Two independent research groups, one led by Andrea Ghez at UCLA, the other by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, turned their instruments toward the galactic center and began, methodically, to track individual stars over many years. Not casually, not for a season or a year, for decades. Year after year, the telescopes recorded the positions of stars very close to the galactic center. Year after year, the data accumulated, and year after year, the picture grew clearer. Stars tracing out their paths, completing arcs, revealing the curvature of their orbits. The UCLA Galactic Center Group, led by Andrea Ghez, carried out these observations over many years, building one of the most precise long-term records of stellar motion near Sagittarius, a star that has ever been assembled. This kind of patience is something that science sometimes requires. There is no shortcut. You simply have to watch and wait and keep watching. What emerged from that watching was a map of stellar orbits, and from those orbits, an increasingly precise picture of the mass hidden at the center. The star S2, a name to rest gently on. Among all the stars tracked near the galactic center, one became particularly important to the story. It goes by the designation S2. In some papers, it's written as S-02. You don't need to hold that name tightly, but it's worth knowing, just for a moment, because its story is the clearest single thread in this whole tapestry. S2 is a star that orbits so close to Sagittarius, a star that astronomers were able to observe it completing a full elliptical orbit, a complete loop around the central object. Not just an arc, not just part of the path, but the whole ellipse, from start to back to start again. That's remarkable on its own. Orbital paths at this scale, in the depths of space, take time. This is not something you can watch unfold in an evening. But when a full orbit is observed, the information it carries is extraordinary. the shape of the ellipse, the speed of the star at different points along it, the period of the orbit. All of these together allow a very precise calculation of the mass at the center, and the calculation, when it was done, returned a result that left very little room for ambiguity. What the orbits tell us about Sagittarius A star, the orbital data from S2 and the other stars near the galactic center, gave astronomers their best current estimate of the mass of the object at Sagittarius A star, something in the region of roughly 4 million times the mass of our Sun. Let that number sit for a moment. You don't have to grasp its scale completely. 4 million solar masses, all of it concentrated in a region of space at the very center of our galaxy, entirely invisible, emitting no detectable light. Now, the question that had to be asked, and was asked carefully, rigorously, was whether anything other than a black hole could explain that result. Could it be a very dense cluster of ordinary stars, too faint to detect individually? Could it be some other kind of exotic, dark, compact mass? The data resisted those alternatives. The mass required by the orbital paths is too large, too concentrated in too small a region, to be accounted for by any known type of non-black hole object that we have evidence for. No visible object has been found at the galactic center that could account for that mass. The conclusion the evidence points toward, carefully stated, as it should be, is that the object at Sagittarius A star is consistent with a supermassive black hole. Here's what we can say with confidence. The orbital evidence for a massive, compact, invisible object at the galactic center is robust, independently confirmed by 2 separate research teams over many years, and holds up under rigorous scrutiny. And here's what we can say with appropriate care. Consistent with a black hole is the right phrasing, because while the evidence strongly favors this interpretation, and while no comparable alternative explanation has been found that fits the data equally well, science speaks precisely about what the evidence allows. That precision is not uncertainty, it's honesty. A Nobel Prize for watching stars move the work of these 2 research groups, watching year after year as stars traced their paths around an invisible center, was ultimately recognized with the highest honor in science. In 2020, Andrea Ghez and Reinhard Genzel were awarded the Nobel Prize in Physics for their discovery of a supermassive compact object at the center of our galaxy. Think about what that means. A Nobel Prize for detecting something invisible, for measuring the presence of something that cannot be seen through nothing more and nothing less than the patient, precise observation of the things that orbit around it. Ghez and Genzel were not awarded the prize because they saw the black hole. They were awarded it because the evidence they gathered over decades made its existence as a supermassive compact object at the galactic center scientifically compelling and independently confirmed. That distinction matters. It says something about how science works. It says something about what evidence really is. If your mind drifts a little here, that's perfectly fine. These ideas don't need to be grasped tightly. Just let them settle. A subtle bonus. What general relativity adds to the story? There's one more layer to this, and it's a quieter, more delicate piece of the picture. As S2 passed close to Sagittarius, a star, at the nearest point of its elliptical orbit, when it was moving fastest through the most intense part of the gravitational field, something was measured that went beyond just the orbital path itself. light climbing out of a strong gravitational field loses energy and shifts toward longer, redder wavelengths, a phenomenon called gravitational redshift, and a specific prediction of Einstein's general theory of relativity. The light from S2, as the star passed through that intense gravitational field, showed exactly this kind of shift, and it was measured and found to be consistent with the predictions of general relativity in a strong gravitational field. This is a quiet but significant moment in the story. It means the evidence from the galactic center isn't just gravitational in a simple sense. It reaches into the predictions of general relativity, and those predictions held. The galactic center is not just a place where stars orbit something massive. It's a place where the deep structure of space-time, as described by general relativity, has been tested and found consistent with what the theory predicts. General relativity predicts that massive objects curve the fabric of space-time around them. The evidence from stars orbiting Sagittarius. A star is consistent with that curvature being present and measurable, even at the scale of individual stars passing through the region. You don't need to hold the technical details. What matters is the shape of what happened, an independent test of a deep theoretical prediction, run not in a laboratory, but at the center of our own galaxy. And it was consistent. The orbital method, quiet, powerful, universal. The orbital fingerprint is, in some ways, the most intuitive of the four we'll explore tonight. It uses physics that has been understood and tested for a very long time. It requires no exotic equipment, just a telescope, a very long baseline of observations, and the mathematical framework that connects motion to mass. And it works not just at the galactic center, but wherever we can track orbiting objects and infer the mass at the center of their motion. The same gravitational logic that keeps Earth in orbit around the Sun. The same reasoning that allows astronomers to calculate the mass of any central body from the motion of objects around it is the logic that revealed the supermassive compact object at the center of our galaxy. We didn't need to see it. We watched the stars around it dance, and the dance told us everything. What orbits can't tell us, and where the next fingerprint begins. The orbital method is powerful, but it has limits, and being honest about those limits is part of what makes science trustworthy. What stellar orbits tell us, primarily, is mass and location. They give us a strong answer to the question, how much is there and roughly where? They don't, on their own, illuminate the structure of the region just outside the event horizon, the intense environment where infalling matter releases enormous amounts of energy. For that, we need a different kind of evidence, a different fingerprint, one that doesn't come from watching stars move in the dark, one that comes from the glow just at the edge of the darkness itself, from the extraordinary heat and light generated by matter falling toward a place of no return. Let's let that settle, and then we'll continue. Because what comes next is one of the most energetic stories in the universe, and it burns brightly enough that we can see it from the far side of the cosmos. Light around darkness, accretion disks, and extreme energy. Even in the darkest place imaginable, the space just outside glows. And that glow tells a story if you know how to listen. The second fingerprint is different in character from the first. It is, in its own way, the loudest signal a black hole can send. Not from inside. Remember, nothing escapes from inside, from just outside, from the region where matter, pulled inward by gravity, piles up and compresses and heats to temperatures that strain the imagination, and in doing so, produces some of the most intense radiation in the universe. Let's slow that down for a second, because this fingerprint begins with a question that might feel simple, but whose answer turns out to be extraordinary. What happens to the stuff that falls toward a black hole? Matter on its way in, the accretion disk. Here's the simple version. When gas and dust in space drift into the gravitational influence of a black hole, they don't usually fall straight in. The material almost always carries some sideways motion, some rotation, and as it spirals inward, rather than plunging directly toward the center, it tends to spread into a flattened, rotating structure around the black hole, like a disk. This structure is called an accretion disk. The word accretion simply means the gradual accumulation of matter. A disk of accreting material, gas and dust, swirling in a vast flattened spiral around the black hole, slowly making its way inward. Now here's where the physics becomes remarkable. As the material in that disk spirals tighter and tighter, as particles of gas crowd closer together and closer to the black hole's intense gravity, they collide, they compress, they rub against one another, and that friction, that compression, generates heat, an extraordinary amount of heat. The inner regions of an accretion disk around a black hole can reach temperatures so extreme that the material no longer just glows in ordinary visible light. It glows across a wide range of wavelengths, including, in many cases, in X-rays. X-rays, the same broad category of high-energy radiation that passes through soft tissue in medical imaging, produced here by gas being compressed and heated in the gravitational field of an extraordinarily dense object. All of that radiation, that heat, that X-ray glow, travels outward. It escapes the accretion disk and moves through space, and it can be detected by us from Earth with the right kind of telescope. A black hole by itself is invisible, but a black hole with an accretion disk, a black hole that is actively consuming surrounding material, announces itself across the cosmos. Let's stay with that for a moment. How we detect it. X-ray astronomy and Chandra. Because X-rays from space are largely blocked before reaching the ground, detecting this kind of radiation requires instruments placed above the atmosphere, in orbit around Earth. One of the most powerful instruments ever built for this purpose is NASA's Chandra X-ray Observatory. Chandra has been used to detect the intense X-ray radiation emitted by matter near black holes, turning the invisible architecture of the universe's most extreme objects into data that scientists can study, measure, and interpret. A black hole cannot be seen, but the process of material falling toward it produces a beacon so energetic that it can be picked up from enormous distances. The darkness, in a sense, announces itself by what it does to everything nearby. When a black hole feeds hungrily, active galactic nuclei and quasars, there are cases in the universe where a supermassive black hole at the center of a galaxy is consuming material at an extraordinary rate, and the results are almost difficult to comprehend in scale. When a black hole at the center of a galaxy is actively and intensely consuming surrounding material, the resulting energetic system centered on the black hole is called an active galactic nucleus, or AGN. In their most extreme form, these systems are called quasars. A quasar is powered, according to the best current understanding, by a supermassive black hole actively consuming enormous amounts of surrounding material. As that material spirals in through the accretion disk, it releases energy, enormous amounts of it, in the form of radiation across a wide range of wavelengths. The result is a source of light so extraordinarily bright that it can outshine the entire rest of the galaxy surrounding it. A galaxy containing many billions of stars can, when its central black hole is in a state of intense feeding, be completely overwhelmed in brightness by the light coming from that single feeding process, not from any star at all. Quasars are among the most energetic phenomena in the known universe. The current best explanation for quasars is that they are powered by supermassive black holes actively consuming surrounding material. This is the model that best fits the observational evidence we have, and no alternative explanation has gained comparable support from the data. Best current explanation is the right framing. Science holds that conclusion with high confidence, and honestly. Jets, the other signature. Some black hole systems produce jets, narrow, highly focused streams of plasma, charged particles that eject outward from the region near the black hole. Not in all directions, like an explosion, but in tight, coherent beams that can extend far beyond the host galaxy and are detectable across a wide range of wavelengths. The jets are not coming from inside the black hole. Nothing comes from inside the event horizon. The jets originate in the energetic region just outside, near the black hole where falling matter and extreme physical conditions interact. The exact mechanism by which these jets are launched and collimated, how the energy is extracted, and how the beam holds its shape over such extraordinary distances remains an area of active research and is not yet fully understood. Several competing models exist, and scientists are working carefully to distinguish between them using observational data. What we do have is clear observational evidence that jets exist, that they are associated with black hole systems, and that they carry enormous amounts of energy outward into the surrounding universe. This combination, the evidence we have alongside the honest acknowledgement of what remains open, is exactly how good science looks in practice. What the glow tells us, reading the disk. Let's come at this from a different angle. The accretion disk glows. It produces radiation, including X-rays, that travels outward and can be detected. But there's more information contained in that glow than just something is hot and radiating. The brightness of the radiation, how much energy is coming out, and at what wavelengths, carries encoded information about the black hole at the center. Models of accretion disk behavior suggest that the spectrum and intensity of the radiation can, in principle, give astronomers estimates of the mass of the black hole, its spin, and the rate at which it is currently consuming material. These estimates depend on the models used to interpret the data, and those models carry their own assumptions. The accretion disk glows is a straightforward observational fact. Here is exactly what the glow tells us about the black hole's spin is more model dependent, and we should hold those conclusions with appropriate care. What we can say clearly, the radiation from accretion disks is real, detectable, and contains information about the systems producing it. Extracting that information reliably is an active area of research, and the interpretations are treated with the precision that field deserves. Where all of this happens, everything we've talked about in this chapter, the accretion disk, the X-ray glow, the quasar luminosity, the jets, all of it happens outside the event horizon. That boundary is where light can no longer escape. What lies just outside it is the most observationally active and energetically extreme environment in the known universe. It's where infalling material compresses and radiates. It's where jets are launched outward with extraordinary force. It's where the density of energy and radiation exceeds anything that exists elsewhere in nature, as far as current evidence suggests. A completely isolated black hole with nothing falling toward it would be genuinely, completely dark. It would be, in practice, undetectable by any current means. But most black holes exist in environments where material is present, where gas and dust drift into their gravitational reach, and the accretion process can begin. And when it does, the black hole's presence is written in light across the sky. That's a second fingerprint. Luminous, energetic, unmistakable. Once you know what you're looking at, a sense of proportion. Let's pause here, quietly, and let one simple idea sit for a moment. The light from a quasar, from a supermassive black hole in the process of consuming surrounding material, can outshine every star in its host galaxy combined. The light you'd see from such an object, looking at it across the cosmos, comes not from stars at all. It comes from the process of matter falling toward a place from which nothing returns. That is what this fingerprint is. That is the scale of the announcement a black hole makes when it feeds. You don't have to hold the full weight of that. Just let the shape of it rest. The edge of this fingerprint, what it doesn't show us. The accretion fingerprint is powerful and luminous. But like all fingerprints, it has limits. It shows us that something enormously massive and compact is present, consuming material and generating extreme energy. It shows us the process happening at the edge of the black hole's gravitational reach. But it doesn't show us the shape of the darkness itself. It doesn't give us a picture of the boundary, the event horizon, or the precise region around it. For that, we need the third fingerprint, one that doesn't come from heat or radiation from infalling matter, one that comes from light itself, from the way that even the most untouchable, unaffected thing in nature, a ray of light traveling through empty space, is quietly, inevitably bent by the gravity of what lies nearby. Let's take a gentle breath, and when you're ready, follow the light, because it's about to take an unexpected turn. Bent starlight, gravitational lensing plus the shadow, EHT. Light always travels in a straight line, unless something enormous quietly bends the road beneath it. The third fingerprint is different in a subtle and rather wonderful way from the first two, because it doesn't depend on anything falling into the black hole. It doesn't require orbiting stars, or heating gas, or consuming material of any kind. It works on light that is simply passing by, light that started its journey somewhere else entirely, heading somewhere else entirely, and was quietly, unavoidably redirected by the gravity of something massive lying along its path. The universe, it turns out, has its own system of lenses, and those lenses are made of gravity. How gravity bends light. The foundation, here's the simple version. According to general relativity, the framework that describes how gravity works at the largest scales, massive objects don't just pull on other objects. they curve the fabric of space-time around them. One way to think about it is this. Space-time isn't a rigid, flat background that objects move through. It's something that can be shaped, and mass is what shapes it. A planet curves the space-time around it a little. A star curves it more. A black hole curves it to an extraordinary degree. Light always follows the straightest possible path through whatever space-time it's traveling in. But if the space-time itself is curved, if the geometry of the space light is traveling through has been shaped by a nearby mass, then the path of that light gets bent too. Not because anything is pushing or pulling the light directly, but because the road itself has changed shape. This bending of light by gravity is called gravitational lensing. It was predicted by Einstein's general theory of relativity, and it has since been confirmed observationally on many different scales, from the deflection of starlight passing near massive objects to the dramatic bending of light by entire galaxy clusters. Gravitational lensing works on any light from any source, as long as a sufficiently massive object lies along or near its path. What a gravitational lens does to the image. Imagine a distant galaxy, far behind a massive foreground object, a large galaxy cluster sitting between us and that distant source. The light from the background galaxy travels toward us, but as it passes by the foreground cluster, the curved space-time around that cluster bends the light rays. Those bent light rays arrive at our telescopes from slightly different directions than they would have if the cluster weren't there. The image of the background galaxy is distorted, stretched into an arc, appearing as multiple separate copies, or in cases of very precise alignment, even as a complete ring of light. These effects, the arcs, the multiple images, the rings, are signatures of strong gravitational lensing. And here's what makes this a fingerprint for invisible mass. You don't need to see the lensing object. You don't need it to emit any radiation. The lensing effect is produced by mass, by the curvature of space-time, regardless of whether that mass is glowing, dark, or entirely invisible. Gravitational lensing can reveal the presence and help estimate the mass of objects that produce no detectable light at all. The light passing near a black hole doesn't care whether the mass is visible. The space-time around it is curved, and the light follows the curve. Near a black hole, where lensing becomes extreme, near a black hole the curvature of space-time is extreme. Far more extreme than anything produced by a galaxy cluster or an ordinary star. Light rays that pass close enough don't just get nudged slightly off course. They get bent severely, redirected by large angles. Some light rays, passing at just the right distance, can be bent so completely that they travel in a circle around the black hole, looping around in an unstable circular path. This region, where light can in principle orbit the black hole, is called the photon sphere. It's worth sitting with that image for a moment. A path that light can travel, circling an object, carried along a curve of space-time. Not a planet, not a moon, but light itself. The photon sphere marks a boundary close to the black hole, where the bending of light reaches its most extreme, and is this region that plays a central role in what the Event Horizon Telescope was able to image. The Event Horizon Telescope, a planet-sized instrument. To image the shadow of a black hole requires a telescope with extraordinary resolving power, the ability to distinguish fine detail at enormous distances. No single telescope on Earth is large enough to achieve this for a black hole shadow. So the EHT collaboration took a different approach. Rather than building one enormous telescope, they linked together a network of existing radio telescopes spread across multiple continents, working simultaneously, pointed at the same target, recording data with extraordinary precision. By combining the signals from all of these instruments, using a technique called Very Long Baseline Interferometry, or VLBI, the collaboration created an effective resolving power approaching the diameter of Earth itself. More than 200 researchers across multiple institutions and countries worked together toward a single image. The result of all this effort was something that had never existed before: the first image of a black hole shadow. M87. The first image, April 2019 asterisk. In April 2019, the EHT collaboration released an image that had taken years of observation, calibration, and analysis to produce. It showed a bright, roughly circular ring of glowing gas, and at its center, a region of darkness. That dark central region is what the collaboration called the black hole shadow. Let's be precise about what that means. The shadow is not a photograph of the black hole itself. The event horizon is not visible in any direct sense. No light comes from within it. What the shadow represents is the region from which light cannot reach the observer because the extreme gravity of the black hole prevents it. The glowing ring surrounding the dark center is produced by hot gas near the black hole. Some of that light travels toward our telescopes directly. Some of it, having passed very close to the black hole, has been bent around it before finally escaping outward. The photon ring, visible in EHT images, is consistent with light that has been bent around the black hole, in some cases going around multiple times before escaping, in line with what general relativity predicts for the photon sphere region. And in the center of that ring, the darkness, the region from which no light arrives because gravity is too strong for light to escape from within it. The object at the center of this image is M87 asterisk, the supermassive black hole at the center of the galaxy Messier 87. The current best estimate of its mass, based on EHT observations, is roughly 6.5 billion times the mass of our Sun. Let that sit gently. 6.5 billion solar masses contained in the dark circle at the center of that image. What the image confirmed: the EHT image of M87 star is consistent with the theoretical predictions of general relativity for the appearance of a black hole shadow. General relativity makes specific mathematical predictions about what a black hole should look like when imaged with a sufficiently powerful telescope. The size of the shadow relative to the mass, the appearance of the bright ring, the way the photon paths curve, and the image the EHT produced matched those predictions. The same theoretical framework that predicted gravitational lensing, confirmed observationally across many different scales and contexts, also correctly predicted the detailed appearance of a black hole shadow, as directly imaged for the first time. That kind of consistency across scales and phenomena and decades of testing is what gives a scientific framework its credibility. Here's what we can say with confidence. The EHT image is consistent with M87 star being a supermassive black hole as described by general relativity. And here's what we can say with appropriate care. consistent with is the right phrasing, not because there is meaningful scientific doubt, but because that is what careful science always says. When evidence matches prediction, the match is strong, the confidence is high, the language is precise. Sagittarius A, closer to home. In May 2022, the EHT collaboration released a second image. This time, the target was the shadow of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. The same black hole whose existence was inferred through decades of watching stellar orbits. The same invisible center around which S2 traces its long elliptical path. The same compact, massive object whose gravitational effect on passing starlight produced a measurable redshift consistent with general relativity. And now, imaged directly, a bright ring, a dark center, the same fundamental structure predicted by theory and seen already in M87 star. Two black hole shadows, two independent imaging results, both consistent with general relativity's predictions for a black hole shadow. The evidence, approaching from this angle, had arrived at the same place as the orbital evidence, the accretion evidence, and the lensing evidence, convergent, consistent, carefully stated. What we see, and what we still can't see. The EHT images represent one of the most technically challenging observational achievements in the history of astronomy. And yet, they do not show us inside the event horizon. The shadow is real. The ring is real. The consistency with general relativity is real. But the interior of the black hole, what lies beyond the event horizon, is not revealed by the image. It cannot be. No light escapes from inside to carry that information outward. The EHT image shows us the edge of the darkness. It confirms the geometry and scale of the shadow. It provides direct visual confirmation that is consistent with the theory. And that is genuinely extraordinary. There is no need to reach for more. The image that exists, a bright ring of glowing gas surrounding a dark center, produced by the combined effort of a planet-spanning array of telescopes, already tells us more than many thought would be possible in a single scientific lifetime. 3 fingerprints converging. We've followed 3 separate lines of evidence now. 3 different fingerprints gathered through 3 entirely different methods, sensitive to different kinds of signals: stellar orbits, X-ray emissions and accretion, gravitational lensing, and the EHT shadow. Each was developed by different groups of scientists using different instruments over different decades. And they all converge, pointing toward one conclusion from 3 completely separate directions. The evidence, taken together, is strongly and consistently in favor of this picture. That convergence is what happens when a scientific picture is genuinely reliable. When it rests not on a single pillar, but is supported from many directions simultaneously. If your mind is drifting gently now, that's perfectly all right. Let the ideas settle where they land. What this fingerprint doesn't cover, and where the 4th begins. The lensing fingerprint gives us a direct visual impression, not of the black hole itself, but of the darkness it creates and the bent light surrounding it. It confirms the geometry. It validates the framework. What it doesn't give us is a way to detect black holes that are completely dark, isolated, with no surrounding gas to glow, no light source nearby to bend. A black hole producing no light of its own, in a region where nothing is falling in, and no background source lies behind it, would leave none of the fingerprints we've followed so far. And yet, those black holes are out there too. The answer came from a direction that no one had expected to deliver it so soon. Not from light, not from any form of electromagnetic radiation at all, from a ripple, a tremor in the fabric of space-time itself, carrying the story of two black holes that merged far away long ago and sent that tremor outward in every direction. The fourth fingerprint doesn't use light at all. It doesn't use orbits or glowing disks or bent images. It listens. And what it heard for the first time changed the way we understand our ability to observe the universe. Let's take one more quiet breath, and then we'll follow the last fingerprint home. Listening to space, gravitational waves plus the open questions. Some discoveries don't come from looking at the sky at all. They come from feeling the faintest tremor in the fabric of everything. 3 fingerprints behind us. 3 independent lines of evidence, all converging on the same conclusion. And yet, there is a fourth. One that arrives through a completely different channel. One that doesn't depend on light in any form. One that can detect black holes that are entirely dark, isolated, producing no radiation and bending no light that we can measure. It detects the tremor left behind when 2 black holes find each other across the void and merge. Let's slow that down for a second. What gravitational waves actually are. Here's the simple version. When massive objects accelerate, when they move, change direction, orbit each other, collide, they can produce ripples in the fabric of space-time itself. These ripples are called gravitational waves. They travel outward from their source in all directions at the speed of light. And as they pass through space, through everything in their path, including us, including Earth, they produce a very slight, rhythmic stretching and squeezing of the distances between things as the geometry of space itself changes. Gravitational waves were predicted by Einstein's general theory of relativity. They were predicted, and then, for a very long time, they seemed almost impossibly difficult to actually detect, because the changes they produce in the distances between things are extraordinarily, almost incomprehensibly small. What produces detectable gravitational waves? The effect is real for any accelerating mass, but the waves become detectable at our current level of sensitivity only when the objects involved are extraordinarily massive, extraordinarily compact, and moving with great speed relative to each other. The most promising sources are systems involving black holes and neutron stars, compact objects of the kind that LIGO was designed to detect. When 2 such objects orbit each other in a tight binary system, they lose energy through the emission of gravitational waves and gradually spiral closer together. Eventually, they merge. And that merger produces a burst of gravitational wave energy, the most intense part of the signal, detectable at vast distances. 2 black holes orbiting each other, spiraling inward, colliding and becoming one. That process produces a gravitational wave signal with a characteristic shape, a rising pitch and amplitude, followed by a sharp peak, then a ring down as the newly merged object settles. And that signal, if it passes through Earth, will cause the distances in our detectors to change by an amount almost too small to state. LIGO, the instrument that changed everything. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. It is, in some respects, one of the most sensitive measuring instruments ever built by human hands. Here's how it works, in broad terms. A laser beam is split into two separate beams, which travel down two long perpendicular arms. At the end of each arm, the beams are reflected back. When the two beams return and recombine, they interfere with each other in a way that is exquisitely sensitive to any difference in the length of the two arms. Ordinarily, the two arms are the same length, and the interference pattern is stable. But when a gravitational wave passes through, when that ripple in space-time causes the geometry of the detector to stretch and squeeze, slightly lengthening one arm while shortening the other, the interference pattern changes. That change is the signal. Now here is where the scale becomes almost difficult to hold. The change in arm length that LIGO is designed to detect, the physical stretching and squeezing of space caused by a passing gravitational wave, is smaller than 1,000th of the diameter of a proton. A proton, the tiny particle at the center of an atom. And the change LIGO measures is smaller than 1,000th of that. This is not a poetic exaggeration. This is the actual engineering reality of gravitational wave detection. Let that settle for a moment. Just let the shape of it rest with you. September 2015, the signal arrives. In September 2015, LIGO detected a signal. It was designated GW 150914. The signal had the characteristic shape of a binary merger, a rising frequency and amplitude, peaking sharply, then fading in a ring down. Its analysis was consistent with the merger of two black holes, with estimated masses of roughly 29 and 36 times the mass of our Sun. Two black holes, entirely dark, producing no light of any kind, invisible to every electromagnetic telescope ever built, announcing their merger across cosmic distances through nothing but the tremor they left in the fabric of space. This announcement was made public in February 2016. The response from the scientific community was something that doesn't happen very often. Not celebration of a result that was expected and overdue, but a kind of quiet, deep recognition that something genuinely new had happened. A new way of listening to the universe, not with light, not with radio waves, not with any form of electromagnetic radiation, with the geometry of space itself. What the detection confirmed, and what it opened. The detection of GW 150914 was the first direct detection of gravitational waves. It confirmed a prediction that had stood in general relativity since the theory was developed. And it confirmed something else, something that hadn't been directly verified before in quite this way. That black holes of the masses involved in GW 150914 actually exist in the universe as merging binary systems. The two black holes that produced GW 150914 were entirely dark. No detectable X-ray emission, no glowing accretion disk, no lensed starlight. The orbital fingerprint, the accretion fingerprint, the lensing fingerprint, none of them could have detected this particular merger. Only gravitational waves could. This is the singular power of the fourth fingerprint. It accesses a channel of information about the universe that is entirely separate from light-based astronomy. Here's what we can say with confidence. The detection of GW 150914 is consistent with the merger of two black holes as analyzed using the framework of general relativity. And here's what we can say with appropriate care. The masses, spins, and distances of the merging objects are inferred from the gravitational wave signal using models. Models that carry their own assumptions. The analysis is rigorous, and the confidence in the result is high, but consistent with, and models indicate, are the right framings for the specific parameter values. The network grows, Virgo, Cagra, and new possibilities LIGO is not alone. Virgo, a gravitational wave detector located in Italy, joined collaborative observations with LIGO, and the addition of a second, independently located detector brought a crucial new capability. With two separate detectors receiving the same signal, each from its own position, the network could begin to localize where in the sky the gravitational waves originated. Cagra, a detector in Japan, subsequently joined the network, expanding the collaboration into a genuinely international multi-continent gravitational wave observatory. More detectors, spread more widely across the Earth, means better localization of sources and improved ability to alert other telescopes to look at the right patch of sky at the right time. This combination of gravitational wave detection alongside other forms of astronomical observation has opened what scientists describe as a new observational window on the universe. One that is entirely separate from light-based astronomy. The universe, it turns out, speaks in more than one language. What the signal encodes, and the honest limits. The gravitational wave signal from a merging binary system isn't just a spike on a detector. It has a shape, a detailed evolving pattern of frequency and amplitude. And that shape encodes information. Models of how binary mergers should behave within the framework of general relativity make predictions about what the signal should look like for a given set of parameters. The masses of the two objects, their spins, their distance from Earth. By comparing the observed signal to these model predictions, scientists can estimate those parameters, the mass estimates, the spin estimates, the distance estimates. These are the outputs of a model-fitting process, not direct measurements. The models are sophisticated, and the framework underlying them has been tested extensively in many contexts, but the parameter values carry uncertainties and are properly reported as ranges rather than precise single numbers. The analysis is consistent with what we'd expect from merging black holes. The confidence is high, and the honest acknowledgement of model dependence is part of what makes the science trustworthy. Dark black holes, the ones only gravitational waves can find. Here's a thread worth pulling gently. Before LIGO's first detection, all of our evidence for black holes came from black holes in environments where something was happening nearby. Stars orbiting them, matter falling toward them and glowing, light being bent around them. Every single one of those fingerprints requires something in the neighborhood of the black hole to work. An orbiting star, an accretion disk, a background light source. But what about black holes producing no light of their own, in a region where no stars are close enough to orbit them, no gas is drifting in, no background source lies aligned behind them, leaving none of the fingerprints we've followed so far? Those black holes are, to light-based astronomy, completely and permanently invisible. Every electromagnetic telescope ever built would see nothing at all in their direction. But if two of those dark, isolated black holes were bound together, spiraling inward over time through the emission of gravitational waves. Then, at the moment of their merger, they would announce themselves, not through light, through the tremor. Gravitational waves from merging black holes allow astronomers to detect black holes that are otherwise completely dark, producing no light or radiation detectable by conventional telescopes. This is what makes the fourth fingerprint genuinely different from the first three. It doesn't need the black hole to be embedded in an active environment. It needs the black hole to move, to accelerate, to interact gravitationally with another massive object in just the right way. The open questions, what we still don't know. We've followed four fingerprints tonight. Together, they build a case for black holes that is robust, independently confirmed, and consistent across entirely different kinds of measurement. But science is not a closed book, and it would be dishonest, and honestly, a little less interesting, to end this chapter without spending a few quiet minutes on what remains genuinely open. The formation mechanisms of supermassive black holes are still not settled. We know they exist. We know they sit at the centers of most large galaxies. We know roughly how massive they are. But how they came to be so massive is an area of active investigation, and the current evidence has not yet settled clearly on one answer. The intermediate mass black hole category is still awaiting clear, definitive confirmation. Evidence is suggestive, and the search continues. But the picture is not yet settled. The exact mechanism by which jets are launched from near black holes, how the energy is extracted, how the beam maintains its coherence over extraordinary distances, is not yet fully understood. The behavior of space-time at the very center of a black hole, where general relativity predicts conditions that the theory itself cannot reliably describe, is unresolved and likely will remain so until a deeper theoretical framework emerges. And the interior of the event horizon, what physically exists or happens beyond that boundary, is, in all likelihood, permanently beyond the reach of any observation using light or electromagnetic radiation. These are not failures. They are the honest edges of the current map, and they matter because they show that the story of black holes is not finished. It is ongoing, with new instruments, new collaborations, and new theoretical ideas continuing to refine and deepen the picture. Science is not a destination, it's a direction. 4 separate lines of evidence, each one developed independently, using different physics, different instruments, and different mathematical frameworks. Stellar orbits, tracked over decades by patient teams of astronomers. Radiation from accretion disks, detected by space-based X-ray observatories. Gravitational lensing effects and directly imaged black hole shadows, captured by a planet-spanning network of radio telescopes. Gravitational waves from merging black holes, detected as a change in distance smaller than 1,000th of a proton's diameter. Each fingerprint tells its own version of the same story, and together, the evidence is strongly and consistently in favor of one conclusion. Black holes are real. They exist throughout the universe. They behave in ways consistent with general relativity, and we have detected them, each time, through their effects, never through any direct light of their own. That's worth sitting with for a moment. We found the unseeable, not by seeing it, by reading everything it left behind. A quiet teaser. What comes next? There's one question that has been hovering quietly at the edge of tonight's journey. One boundary we've circled without crossing. The event horizon itself. We've described it carefully. A threshold, a point of no return, the boundary beyond which light cannot escape. We've said what happens just outside it, where all the observable physics takes place. But what does crossing that boundary actually mean? What does general relativity say about the nature of space and time in the region around it? Approaching it, as understood through our best current theory. What are the theoretical ideas, carefully distinguished from confirmed observation, about what might exist in that territory? And where exactly does our reliable knowledge end and speculation begin? These are the questions that will carry us into the next episode. The event horizon is not just a boundary in space. In the framework of general relativity, it's a boundary in the structure of space-time itself. And what that means, explored carefully and honestly, is a story that deserves its own quiet night. For now, let those questions rest gently at the edge of your awareness. You've followed the fingerprints all the way to the edge of the darkness tonight. What lies at that edge and what it means, that's where we'll begin next time. You've followed the fingerprints of something invisible tonight across time and space and silence. And now it's time to let all of that settle softly into rest. Take a breath in, slow, easy, all the way down, and let it go. You don't need to hold any of it. Not a single word, not a single idea. Everything you heard tonight can drift now, loosely, like something released into still water, moving wherever it wants to move, without you needing to guide it. Just breathe. Imagine, if you like, that you're somewhere very high up, not falling, just floating, suspended gently above everything, above the cities, above the clouds, above the soft blue curve of the world below. It's quiet here, not the quiet of emptiness, but the quiet of something full and unhurried, the kind of quiet that holds you rather than leaving you alone in it. The stars are out, not dramatic, not overwhelming, just present, scattered across the dark the way they always are, steady, patient, each one doing whatever it is a star does in the long, long hours of the night. You don't have to name them. You don't have to know anything about them. Just let them be there. Somewhere out in that dark, unimaginably far away, there are things we can't see. They make no sound we could hear with our ears. They carry no color, no warmth, no outline against the sky. And yet, they are there. We know, somehow, through all the careful, quiet work of people who spent their lives paying attention, that the darkness is not empty, that it is full in its own way, that invisible things leave their marks on everything around them, the way a stone dropped into still water leaves rings long after it's gone beneath the surface. That's a kind of comfort if you let it be. The universe is larger than we can hold, and somehow we've found our way to the edges of it, not by force, not by noise, but by patience, by watching, by listening for what the silence was trying to say. Let your body be heavy now. Feel the weight of your limbs, gentle and solid, sinking into wherever you're resting. There's nothing you need to do with your hands. Know where your feet need to carry you. Let your shoulders drop a little more. They've been doing a lot today. Let your jaw unclench if it crept back into tension somewhere along the way. Let your eyes rest completely, behind closed lids. Nothing to watch, nothing to follow. If thoughts come, that's fine. You don't need to push them away. Just notice them the way you'd notice something drifting past on a slow river, and then let the current take them on. You're not in the river. You're on the bank, watching, warm and still. The thoughts will move. They always do. Somewhere in the deep, unhurried dark, something enormous and silent turns slowly on its axis, not watching you, not needing anything from you, just turning. The way things turn when they've been turning for longer than we have words for. And the light around it, that soft, ancient glow, Aden, bends gently inward, not rushing, just following the shape of things, the way water follows the shape of the ground beneath it, the way breath follows the shape of the lungs that hold it, the way sleep follows the shape of a mind that finally lets go. Let go now. There's nothing left to figure out tonight, nothing to solve, nothing to remember, nothing to carry into whatever comes next. The questions that remain open will still be there in the morning, patient, unhurried, exactly as interesting as they were before you closed your eyes. But right now, they can rest, and so can you. The dark is friendly tonight. It isn't empty, and it isn't cold. It's full of things that have been waiting patiently for someone to notice them. And tonight, quietly, you did. You followed the clues. You stayed with the story. You let the universe be as strange and as large as it actually is, without needing it to be smaller or simpler than that. That's no small thing. Let your breathing slow, just a little more. In and out. In and out. Each breath a little quieter than the last. Each one carrying you a little further from the busy parts of the day, a little deeper into the soft, unhurried place where sleep lives. You're almost there. You've been almost there for a while now, if you're being honest. The stars are still out. They'll be there when you wake up, on the other side of the dark. Though you won't be able to see them in the daylight, they don't mind. They're patient like that. And somewhere much further out than the stars, in the deep quiet of a universe that is far older and far stranger and far more interesting than anyone fully understands yet. Things are turning, things are glowing, things are pulling other things gently toward themselves, the way everything massive does, and it's all fine. It's all in its unhurried way, exactly as it should be. Now close your eyes and gently replay the universe you heard tonight, and rest.